You know, for the longest time, the story of AI has been all about one thing: scale, right? Bigger models, more data, more compute. Just more. But what if the next giant leap forward isn't about getting bigger, but getting smarter? Let's get into it, because we're seeing this incredible shift away from just brute force and towards truly brilliant design. And it's changing everything about how we build AI.
Okay, so here's the plan. First, we're going to talk about AI's big scaling problem, why we're basically hitting a wall. Then we'll look at the secret sauce that made today's deep learning even possible, and expose a couple of major flaws hiding inside. From there, we'll check out the amazing architectural breakthroughs that are fixing those problems. And finally, we'll wrap up with what this all means for the future of AI. Sound good? Let's go.
All right, first up, the big problem: the elephant in the room. As these AI models get bigger and bigger, we are slamming right into a very expensive and honestly a very frustrating wall. Let's be real here. The way we've been doing things just isn't sustainable. This whole race to just keep scaling up has built a system that's, yeah, incredibly powerful, but also incredibly fragile. The costs in time, money, and energy are just exploding, and all the signs are pointing to the same conclusion. Just piling on more layers isn't the answer anymore. And the stakes here are huge. We are talking about massive amounts of money, energy, and compute just poof, gone to waste. One of the papers we looked at describes how these giant training runs can just suddenly collapse. I mean, imagine this. You've got a multi-million-dollar process chugging along, and then bam, it just fails out of nowhere. This isn't just some minor bug. It's a colossal waste of resources, and it's seriously holding back progress. Okay, so to understand how we fix this, we've got to go back and look at the brilliant little trick that got us this far in the first place. It's a really elegant idea, and it's basically the backbone of almost every single modern AI model out there. It's called a residual connection, but you'll also hear it called a skip connection. And the idea is, well, it's simple, but it's totally revolutionary. See, instead of forcing information to go through every single layer, one by one, you create a shortcut. This little shortcut lets the signal from an early layer literally skip ahead and get added back in way down the line. And that simple trick, that's the reason we can train these incredibly deep networks at all. This is a perfect way to visualize it. Think of the neural network like a long road trip. The main road has you stopping in every single little town, every processing layer. But the skip connection, that's the information superhighway. It's the express lane. It lets the really crucial information just zoom past all the traffic jams and potential slowdowns, making sure it gets to the end of the journey, deep inside the network, totally intact. But, and here's the big twist, this superhighway, the very thing that made all this progress possible, has a couple of hidden, really critical flaws. And as our models get bigger and bigger, these flaws are starting to cause some absolutely catastrophic failures. So let's break these down. First up, you've got information dilution. The best way to think about this is the cocktail party problem, right? Imagine you're trying to hear one important conversation, but you've got dozens of other voices all yelling at the same time. The important stuff just gets drowned out by all the noise. And that's what's happening here. The network adds everything together, and the truly useful signals get lost. Then, you've got the total opposite problem: signal explosion. This is basically a game of telephone gone horribly wrong. As the signal passes from one layer to the next, it gets a tiny bit amplified. But when you do that hundreds of times, well, one paper found that the signal was getting amplified by a factor of 3,000. It's just total chaos, and the whole training process just collapses. So, we've got a serious problem. The very foundation we've built all these incredible models on is fundamentally unstable. If the backbone itself is broken, how in the world are we supposed to build stronger, deeper, more reliable AI? Well, that is where these new breakthroughs come in, and this is the exciting part. Researchers are now totally re-engineering the connections themselves. They're creating smarter pathways that get right to the heart of these problems. Okay, solution number one is called DeepCrossAttention, or DCA, and it's designed to fix that cocktail party problem. So instead of just mashing all the previous signals together, DCA gives the network the ability to selectively listen. It actually learns which signals are important and which ones are just noise, so can focus on what really matters. And hey, the proof is in the pudding. This data comes straight from the research paper. They're comparing different models on a language task, and the number you want to look at is perplexity. For that, lower is better. And would you look at that? For about the same model size, DCA scores an 18.06. That's a huge improvement over the standard transformer model. It's just plain smarter and more efficient. All right, what about that other problem, the game of telephone where the signal just explodes? The solution for that is something called Manifold-Constrained Hyper-Connections, or MHC for short. The best way to think about this is like adding mathematical guardrails to that information superhighway. It literally forces the signal to stay in its lane and not spiral out of control. Yeah, this quote here really nails it. It talks about restructuring the layers by constraining them inside a mathematically defined manifold. Now that sounds complicated, but all it really means is that instead of letting signals run wild, MHC puts them in a kind of mathematical safety zone. This makes sure that no matter how deep the network gets, the signal stays stable. It's not a small tweak, it's a fundamental change to how the network is built. And just look at the difference this makes. It's incredible. The research found that in a standard model, that signal amplification could spike up to a factor of 3,000. I mean, that is pure chaos. But now look at the bar on the right. With MHC's guardrails in place, that amplification gets slammed all the way down to 1, a perfect, stable 1. The chaos is completely, totally tamed. So what's the big takeaway here? What does this all mean for the future of AI? Well, it signals a massive shift in thinking for the entire field. We are moving away from the old mantra of bigger is always better to a new one, smarter is better. I mean, the bottom line is these new designs deliver real-world wins. You get models that are more efficient. They can do more with less. You get way better training stability, which means way fewer of those crazy expensive failures, and all of that saves a ton of money, time, and energy. But the most important thing is shifting the focus back to smart design, what the experts are calling macro architecture. It's all about the big picture blueprint of the AI. And that leaves us with one last big question to think about. For years, every headline was about how many billions or trillions of parameters the newest model had. But as we look to the future, is the next AI revolution going to be measured not by its sheer size, but by the sheer cleverness and elegance of its architecture?